The final quantity to learn about in this chapter on work, power, and energy is power. And we did talk about this in ninth grade, and what you learn now is not all that much more or different. If you ask me, what's the absolute most important thing to know about power? If I don't want to learn it all, if I just want to learn the most important thing, so I'm most likely to get a problem right, it'd be what I put here. Think joules per second, and that will help you no matter what aspect of power you're looking at. But joules here, joules could mean work or energy. Both work and energy have units of joules. So what does this mean? Work per second or energy per second? So that's what these notes will explain. And to understand this, to understand the answer to that question, we have to adopt what's called the energy viewpoint that was developed in the 1800s. And instead of starting with the idea of work, we start with the idea of energy. So we start with the idea that energy can take different forms or be in different types: kinetic, gravitational, spring or elastic energy, chemical energy, thermal energy. And then here's what work is. Work always indicates a change in energy, and we can represent that by delta E. So whenever there's work, there's always a change in energy of some sort. But not every change in energy involves work. This is not really part of the current chapter, so I'll just mention it briefly and go on. An example would be nuclear energy changing into electromagnetic energy. No actual work is done there, but you do have a change in the type of energy. All right, so we're talking now about change in energy. This can happen in a couple of different ways. You can have an energy transfer, so from one object to another. For example, if one billiard ball or one ball hits another ball, so there's one ball, here's a second one. Okay? And if I do this right, the first one stops pretty much. But what we see is a transfer of energy from one object to another. That's an energy transfer. That's one way you can have a delta E. Before picture, after picture, here's a ball on a pool table. This one's stationary, this one's moving. They collide, and afterwards, this one's stationary and that one's moving. So we say that the first one has transferred kinetic energy to the second one. The second way we can have a change of energy is a change of type, possibly within the same object. Not necessarily a transfer from one object to another, but a change of type within an object. For example, this wind-up car. I back it up, and it acquires elastic energy because it has a spring inside. And when I release it, that elastic energy changes into kinetic energy. So that's my example, elastic energy changing into kinetic, or both. You could have a transfer of energy and a change of type in the same action. That's very common. For example, if I throw a baseball, the energy starts as chemical in me and eventually becomes kinetic in the baseball. All right, here's an example to think how to think about this as energy changing. Let's say I climb vertically, and let's make my mass 80, because right now it's closer to 80 than it is to 70 after all the quarantine and not running and eating a lot of desserts. So my energy is 80 kilograms, and let's say I climb vertically 3 meters in 6 seconds at constant speed. What's my change in energy? Well, the only type of energy I'm gaining based on this chapter is gravitational energy, and we can calculate using the formula that I've gained 2,400 joules of gravitational energy. But whence? And whence is a fancy old-fashioned way. Where from is a little less old-fashioned, but it means from where. And for when you read older English, here's a little chart for what these, and you can see the patterns in this. If you like patterns, if you're one of those people like me, then this is all very patterny. See the H's across the top, TH and WH? If you have the idea of from, hence means from here, thence means from there, whence means from where, and so forth. And this is, hither is to here, to there, to where, etc. So this is, you'll see this in Shakespeare and in older English and in modern people, in movies about older times. People trying to be funny, they'll use these words, but you'll see there's a complete structure to it. It's a pattern. We've replaced these for the most part today with the prepositions, but that's how it was structured in older English. Okay, so whence? What were we doing? Oh, that's right. So I climb 3 meters at a constant speed, 80 kilograms, and I gain 2,400 joules of gravitational energy. Where did it come from? Well, I burned calories, so we say it came from chemical energy. So we say there's a delta E, not because we've added or subtracted energy to the total of the universe, but because it's changed type. 2,400 joules of energy has changed from chemical into gravitational. All right, that sets us up to understand the concept of power. So here's what to know about power. As I said before, the most important thing to know is the concept of joules per second. Since it's joules over seconds obviously is the amount of time that goes by, so we'll put a delta T down there, that's seconds. But joules could be work or a change in energy. Not energy, it's not energy over time, that doesn't really make sense. But the change in energy divided by how much time goes by. And work indicates a change of energy. So if you can figure out the work for something, you could do joules of work per second of time. Or in a different problem, you might be given a change in energy. So you would use change in energy per second of time. And if energy is a continuous function of time, if energy equals some function of time that would be given to you in a problem, then the power at any instant would be the derivative of energy with respect to time. Okay? Now notice, you're dividing by delta t or dt, which means this is a rate, in the purest sense of the term a rate of change with respect to time, or what some scientists will call a time rate of change. Power is a time rate of change of energy, so it's a rate of change of energy with respect to time. The symbol for power is a nice convenient capital P, which is also the symbol for pressure in science, but normally you won't have those two in the same problem, and in AP Physics we definitely won't have pressure in this chapter, and if it comes up at all, it's not part of our course, but just as part of your science literacy, you're supposed to understand that pressure is force divided by area. Right? The unit for power, as I said earlier, the most important thing to know about power is to keep in mind. When you hear power, first thing you want to think is joules per second, and the rest can follow from that. But the joules per second has been renamed. This is our standard metric unit, and has been renamed the watt, after James Watt. Right? And since it's named after a person, the symbol for the watt is a capital W, not a lowercase w. There's a non-metric unit for power that is very common in the United States and also in general in automotive engineering, and that's the horsepower. And 1 horsepower is equal to 746 watts to 3 significant figures. That's not exact, but that's the 3 significant figures. Okay, so let's look at my example. In my example, we found that the amount of energy gained in gravitational and lost in chemical was 2,400 joules, and it took 6 seconds. So you just do delta E over delta T, and you get 400 watts. A little bit more than half a horsepower. And that's typical. A good athlete can generate a whole horsepower, but only for a few seconds. Maybe 10, 20, 30 seconds at most. A horse can perform 1 horsepower of power indefinitely, really, at a casual workload over definitely an hour and definitely for several hours, an average size horse. All right, and then finally, sometimes it's not all that easy to measure joules directly. Right? We don't have a joule meter most of the time to measure joules. And so there's an alternate formula for power which can sometimes involve things that are easier to measure or that we care about. If the force is constant, you could write power like this. Change in energy or work done over time, but work is force times distance. Now we have a change in position. I said force times distance, of course it's delta x. Change in position divided by amount of time change. Well, look at this, delta x over delta t. That's just the speed in one direction. So if everything is in one dimension, if the force is in one dimension, and if the motion is in one dimension, the power is just the product of the force times the speed. What if you're in 3 dimensions? Well, then the angle matters, and you're dealing with a dot product. So in 2 or 3 dimensions, and remember 3 dimensions includes 2, so it might be I, j, k, or it might be I and j. You do a dot product between the force and the velocity vector, and that gives you the power. This could be average, if you're dealing with an average force, an average velocity over a period of time, or it could be instantaneous, if you know the force like right at t equals 2 seconds, and the velocity right at t equals 2 seconds. Because this is a rate, it can be instantaneous. It doesn't have to be accumulated over a certain amount of time. So this could be, I don't go into any details or do any problems on this because it's a minor point in AP Physics, but you may see problems about this in the book or in the review packets, and this is your general alternative formula, good for 3 dimensions and good for instantaneous calculations or average calculations. All right, in case you care, power is one of the more important topics, one of the more important quantities we deal with in the sense that you can immediately grasp why it's important. First, it describes motors. For instance, my wife's Tesla has a dual motor long range. That means it has an electric motor on each axle. And its total power production is 200,000 watts. That means it theoretically can produce 200,000 joules of energy every second. Say when we're accelerating, it's changing, every second it's changing 200,000 joules of electrical energy in the battery into kinetic energy in the car. My old Cavalier, however, from 1996, has a more anemic power rating of about 90,000 watts, so less than half of the power of the Tesla Model 3 long range. All right, so one reason power is important, that's the number one, the most important way we describe motors. Of course, there are other things important about motors. For example, RPM, how rapidly they spin, their size, so whether it can fit in the machine that you're building. But the number one thing we use to describe a motor is its power rating. Second, think not so much about producing power, but about consuming energy. Not so much about producing energy per second, but about consuming energy per second. For example, you have electrical energy coming into your house through the electric wires, the electric outlet, and it changes into different types of energy. For example, light energy in your computer, chemical energy stored in the battery of your cell phone, thermal energy in your stove. So your parents pay for that. And power tells us energy is what you pay for. So when you get a statement from the electric company, it'll basically tell you how many pennies you pay per joule. Or really, it's the other way around. There's like thousands and thousands of joules cost 1 penny. So energy equals money, not force, not distance, not time. What you pay for when you pay money is energy. And that's why energy is such an important topic. I think it's the most important quantity in science because it has historical, economic implications, political implications, but energy equals money. So since energy equals money and power tells you joules used per second, power can be converted into figuring out money spent per second. That's the second reason that power is such an important quantity for people who, say, run a business or are designing a machine, because it's, in a sense, literally telling you dollars per second. All right, at this point, with these notes, you are able to do homework number 6. I will put the assignment in Cavnet and tell you when it's due.